Good morning, everyone, and welcome to the 12th EURODOS webinar and the second webinar organized by the Working Group 11. The focus today is the presentation of the project CRREAT, that is an action of Research Center on cosmic ray and radiation events in atmosphere. Before leaving the floor to the speakers, I want to briefly introduce the Working Group 11 that, as I told you, organized this webinar. The chairperson is myself, and the secretary is Veronica Osokova from Eli Beamline. We count on 37 full members coming from 10 countries, and a variable number, around 50 corresponding members who collaborate to the working group activity. The main motivation is increased knowledge about high energy radiation field, and all these the action are actually in this direction. We are organized in 9 tasks related to computational dosimetry on board aircraft, or in case of solar flare, that are the task 1 and task 3. We have a task devoted to dosimetry in pulsed field. We have other tasks related to cosmic radiation, not computational in this case, but for measurement of solar particle events or radiation induced by natural activity in the atmosphere. By the way, this task 4 and 8 will be the topic of this seminar. We have a task active in high energy reference field, and other tasks again for aircrew dosimetry. One task, the task is 11, that is an education action about a course on unfolding that is coming soon in July. And a task for benchmarking Monte Carlo models, especially for high energy neutrons. These are the main activity of the Working Group 11. Coming to the webinar of today, this is the agenda. So after this short introduction on the Working Group 11, I leave the floor first to Andrei Plock and then to the next speaker. Just for organization, there will be a Q&A section after each talk. So feel free to write your question in the Q&A chat, and I will moderate the discussion. So I don't dwell any longer, and I leave the floor to Andrei Plock for the first talk. Please, Andrei.
Okay. Good afternoon, ladies and gentlemen. Thank you very much, Marco, for introducing me and for the welcome talk. My presentation title is General Notes about CRREAT and radiation dosimetry measurements on board aircraft. And actually, this title is also a brief outline of my presentation. So my name is Andrei Plock, and I am from the team of CRREAT, and which is the project at the Nuclear Physics Institute of the Czech Academy of Sciences. I'm also active member of EURODOS Working Group 11, and especially in Task 8 and Task 4. So this is our scientific team of CRREAT. So there are 5 students, PhD students, 2 postdocs, 8 senior researchers, 1 technician, and 1 key foreign researcher. So currently, key foreign researcher is Lembit Sichwer. He is the one on the first photo on the left, and he's from Sweden. Our first key foreign researcher was Professor Kudela. He helped us very much and with the preparation of the whole project. And Professor Kudela, he's also the one who built up the neutron monitor on Lomícký štít Observatory in Slovakia and High Tatras. And unfortunately, 6 years ago, he passed away. Our second key foreign researcher was Dr. Ginter Weitz from DLR, and he had to, from health reason, he had to leave our project. And we also had some excellent foreign researcher, Dr. Eric Benton from Oklahoma State University, who supported our team in 2019. So I thank very much to all our members who already more than 6 years or about 6 years work on this topic of the project CRREAT. So the CRREAT project is the research center of cosmic rays and the radiation events in the atmosphere. Here are some more project details. So the funded period is from December 2016 to October 2022, but probably it will be prolonged due to the COVID in last years. Our research domains are 3. So the first is dosimetry of ionizing radiation in atmosphere, which has the cross-section with working group 11 of EURADOS. Second research domain is physics of storm clouds and upper atmosphere phenomena. This topic is covered by the Institute of Atmospheric Physics. And topic number 3 is characteristics of the electromagnetic field in the atmosphere, which is covered by Czech Technical University Faculty of Electroengineering. We have quite a big scientific advisory committee, about 12 members from several countries like Armenia, France, Germany, Japan, Russia, and USA. And objectives of our project are basically 2. So first is to observe relations between the atmospheric phenomena and ionizing radiation. Here we have 2 sub-objectives to find suitable methods for detection and dosimetry of thunderstorm radiation. And second is clarification of the causes of lightning discharge initiation. It's quite interesting that this is still not clearly described. Second objective is to clarify the phenomena causing variations of secondary cosmic particles. And there are also 2 subtopics which partially also cross-section with working group 11. So influence of the atmospheric status on the secondary cosmic particles detection, like water in the atmosphere, I don't know, pressure and so on. And also the understanding of quasi-periodic and fluctuating phenomena in cosmic ray detection. Okay, so this is a nice figure which summarizes the radiation phenomena that occur in atmosphere, and also it summarized the measurement platforms used in our project. So from the right, the GCR is shortened for galactic cosmic rays. So it came from far galaxies and interact with atmosphere. Mainly it is protons from about 98% and helium ions and some heavier ions. And the secondary cosmic radiation creates the cosmic ray showers, so-called cosmic ray showers in the atmosphere. And there is composed of neutrons, protons, electrons, positrons, muons, gamma, and etc. pions. And composition and intensity vary with altitude, location, and solar activity. It's quite interesting that with higher solar activity, we have lower doses of galactic cosmic radiation due to a stronger magnetic field of sun. In the case of solar energetic particles, SEP, which is also mostly protons, the source is coronal mass ejections or solar flares, and it can cause increases on Earth, and then we call it ground level enhancements, or decreases, and then we call it Ford-Bush decrease. Another big source in the atmosphere, which we are interested in our project, is thundercloud with positively and negatively charged areas, which works as the biggest natural accelerator in the world, and thus it is a source of ionizing radiation. Several radiation phenomena have been described relating to this thunderstorm radiation. So first was TGF, which is terrestrial gamma ray flashes, and another is REA, which is relativistic runaway electron avalanches. These electrons can be accelerated to high energies of several mega electron volts, or several tens of mega electron volts, and then they produce the TGFs. This is the probably source of the gamma radiation, the Bremsstrahlung from these electrons, which go through the matter of air. And another is terrestrial ground enhancements, which is radiation measured on ground. I will talk about it a little bit later. The TGFs has high energies enough to trigger gamma N reactions, so they produce also terrestrial neutron flashes. So this is also something which is described in the literature, and we are interested in it. Concerning platforms, so from up to down, we have detectors on spacecraft in International Space Station, on CRREAT Air satellite, and some others like Lucky 7, and we also plan to have different missions, but due to the current difficult situation with Russians, we probably have to change our plans. Another platform is stratospheric balloons. You will listen lecture about it today, and also aircraft and drones, measuring cars, and mountain observatories. So in the Czech Republic, we have a mountain observatory on Milešovka, which is 837 meters tall. So in the case of thunderstorm radiation and gamma radiation, mostly there are two phenomena described. They sometimes are called short and long bursts. So the short burst is called terrestrial gamma ray flashes, which is intense sub-millisecond flash of gamma radiation. As I already said, it's a Bremsstrahlung from relativistic runaway electron avalanches. It can have a few 10 to 17 gammas with energies of several mega electron volts or higher, and it was observed basically on satellites. And firstly, it was discovered in 1994 by the BATSE satellites, which focused on gamma ray flashes from space, but they occasionally see the radiation coming from the Earth. The figure on the right I borrowed from Carlson, and it shows that the magnetic field is not necessarily to be inside the thundercloud, but also around the thundercloud. So the relativistic electron avalanches can occur also outside the cloud and trigger the gamma rays, TGFs. Another phenomenon is thunderstorm ground enhancements, also called long bursts. So it's prolonged rise of gamma ray intensity. It has about a minute scale duration, and it preceded a negative field variation because lightning discharges stop the electric field. So this is basically measured on ground, and we have several on-ground measurements, and we will listen nice lecture today about it. And we must distinguish it from so it's different from radon progenies washout. There is a big difference with this. Another interesting is Thunder's nuclear reactions, which is described on this figure, brought from the Enoto, Teruaki Enoto et al. From Nature. So they describe the nuclear reactions triggered by the gamma rays, TGFs. So gamma rays with energies higher than 10 MeV interact with nitrogen-14. One neutron, fast neutron, is released, and then is moderated in the atmosphere, and then can be captured and by nitrogen and the excitation of gamma rays. Another process is that the rest of the nitrogen is nitrogen-13, which is unstable, and it further decay to positron and carbon-13, which is stable. Positron then annihilate, and we can measure the 511 kiloelectron volt gamma rays on ground. This process takes some time because the half time of the decay takes some several minutes, and so then it goes with the thundercloud, and we detect it in the detector. And this was observed and described in a special thunderstorms in Japan, in winter thunderstorms, where the cloud is very low altitude, about 1 kilometer only above the ground, above the sea level. So now I came to the second part of my presentation, which is about the radiation measurements on board aircraft. The motivation for the dosimetry on board aircraft is that the only galactic cosmic rays is taken into account for routine aircraft crew dosimetry, and it is calculated by computer codes. And as we can see on the figure on the right side, there is where is the radiation dosimetry of aircrew from 1997 to 2020, and the maximum effective dose measured in Czechia was 6 millisieverts per year, which is actually the highest doses, and also the average effective doses are the highest of aircraft crew in comparison with other radiation workers. Also taken into account the solar particle events that occasionally can have even doses higher than 1 millisievert per hour, but in a routine aircraft crew dosimetry is not taken into account. The good thing is that such high solar particle events don't occur often. It's very quite rare. On the other hand, someone has calculated that terrestrial gamma ray flashes can cause very high doses, up to 30 to 100 millisieverts per event. So this was a big motivation for us to really try to measure it on board aircraft. There are many difficulties of measurement of it. The most important of them is that pilots go out of the thundercloud. They don't go to the thunderclouds, so to really measure such high doses is difficult. But sometimes to save the fuel and so on, they risk and they go through the thundercloud, and then it can happen. Yes. For example, commercial aircraft is hit by about 1 lightning strike per year or average, but not every lightning generates TGF. So if we do some more statistics about it, so for example, measured with satellites, it was that for 2,600 light lengths, only 1 TGF occur. So if we calculate it, so we can came to the conclusion that every 10 to 30 days, an aircraft might be near TGF and potentially exposed, which is quite often to such high doses. Another motivation is that the effect of solar particle event is or solar energy particles is that it can increase the dose rate up to 3 times or even higher. So it can it is also quite important. So this measurements was done by our group in 2001 on April 15th, and the event called ground level enhancement 60. It was measured by Professor František Sporný. So based on this, we have developed the dose evaluation method for the thunderstorm radiation. So first, we must do the proper dosimetry of cosmic radiation. For this, we need a good calibration of our detectors, and also we should install it on board aircraft and to have good statistics and to have the long-term monitoring. And also we do some intercomparison flight campaigns with also other groups, yes, to intercompare these detectors. Second point is the selection of a suitable detector of the thunderstorm radiation. So we did it. We have some gamma spectrometers, and also for the muon detector, we have the good detector. Number 3 is the radiation test at artificial lightning conditions. This is also campaigns organized by our group in Prague. And we also do radiation measurements using balloon and UAVs. This will be talked by Eva Ambrožová today. And we also do some on-ground detection of the thunderstorm radiation phenomena with special detectors used in the world, and like Sevan network and so on. And also, based on this, we came to the radiation dosimetry on board aircraft. So long-term monitoring on board aircraft we perform since 2001 with detector Lulin, and also in the last years we developed under the CRREAT project detector ERDOS with the same silicon diode, pin diode, and it's installed several units in aircraft. We also developed some, so these detectors should be comparable, about which is this slide that and paper by Kakona, Stepan et al. Comparative measurement of mixed radiation fields, which show that Lulin and ERDOS have comparable results. So the database can be used for both detectors. And another type of detectors also are included in the databases. So now newly we installed PyTED, the newly developed detector with plastic scintillator, and also ERDOS-C with a scintillation crystal and silicon photomultiplier. For muon detection, we have stripe detectors, and there are the 4 layers working in coincidence. We have 2 databases, EDNA and CR10, and the databases are important for simple access to data for all and to compare measured data with calculation using codes during interesting events. So I showed this. Here are some details about the PyTED detectors, which is focused on measurements of neutrons, and plastic scintillator supports both shape discrimination for discrimination of neutrons and low LET component. ERDOS-C, we have tested 2 types of scintillation crystals, with sodium iodine and so-called crystal called CRREAT 19, and here are some comparisons. So I go a little bit more quickly. So concerning the flight campaigns which were done in a CRREAT, so one of them was Reflect, which is a research flight of Eurados and CRREAT. The first one was in November 2017 with ABS Jets Embraer Legacy. And there are many institutes, 12 institutes participated in it, and more than 250 kilograms of instruments were on board. And main aims were intercomparison, validation of codes, and test of novel dosimetry methods. The related paper was published last year by Eva Ambrozova. We repeated such measurements in the case of Reflect 2 and Reflect 3. This time it was not in our coordination, so we only participated in the flight. So it was shorter flight duration, but the same route and different detectors, and the paper is in preparation. But now is ready passive Reflect with passive detectors, which is under the action of task 4. Intercomparison of passive detectors on board aircraft, because the radiation field on board aircraft represents a very nice and interesting field for intercomparison of methods with passive detectors. So it will be installed there for several months, maybe 1 year, and it should start next week. The box is ready. It will be also active detector, but more for intercomparison, but most of them will be some TLDs, OSL, RPL, also D-shuttle detectors, and CR39. So finally, when we have all data, we also must have data. We want to install as many as possible radiation detectors to have higher possibility to detect TGF on board aircraft. So by now we have contract with Czech Airlines, Smartwings, IBS Jets, Airstream Jets, and these Czech airlines. And we also have to always know where the detector recorded the data. So we have to have the flight path. The easiest way is to have the GPS on board, but sometimes it's technically difficult. So then we rely on data from company or also from the ADS-B receiver, and we have some special access to the database of Flight Radar 24. So for conclusion, so radiation, so we have the hypothesis that radiation phenomena in thunderstorms can pose serious radiation risk to aircrew and passengers. So the project CRREAT focuses to prove it by radiation measurements in different altitude levels. And we developed a method for evaluation of dose equivalent cost of thunderstorm radiation on board aircraft, and the first steps were made. So we also organize several flight campaigns for open for scientific community, and we wish to repeat it again. And for future step, we want to equip as many aircraft as possible with dosimeter sensitive also to high energy gammas. Thank you very much for your attention, and I apologize for a little longer talk. So I'm open for questions now.
Thanks, Andre, for your very, very nice presentation. There is a question by Rémi Galliard. That is, what is the maximum dose rate in silicon associated with the TGF as a function of the distance?
Oh, thank you very much. It's a nice question. So I must say that we don't have data yet. We didn't detect any TGF, and I don't think that we will detect something with the silicon detector. Actually, the silicon detector is is there to measure the cosmic radiation, and we have methods to convert the dose in silicon to dose equivalent or ambient dose equivalent. But for TGF measurements, now we newly developed another detector with sodium iodine crystal, and this one is now installed on onboard aircraft. And also we have the plastic scintillator, which is not that much sensitive to it, but also it can distinguish between the gamma rays and neutrons.
Okay, thanks. I cannot see, no, yes, Dennis Santos just posted the question. Do you plan on investigating the effect of the South Atlantic magnetic anomaly on archaeodosis?
The effect of South Atlantic anomaly. On board aircraft, I don't think that we can see it, but on the spacecraft, we have already detected it with the detector space dogs, and I think this will be presented by Marek today. That yes, we did see it.
Okay. I cannot see any other question, so we can move to the next speaker, who is Ivan Rozova. So, Iva, the floor is yours.
Okay, thank you, Marco. So, good afternoon. I will talk about radiation measurements using stratospheric balloons and drones. As you already heard in Andrei's presentation, one of the aims of the CRREAT project is to measure cosmic radiation at different altitude levels. And for this, we need a suitable platform. So for lower altitudes, UAV, and especially for high altitude, stratospheric balloons are a very useful tool. So they provide a platform for measurements of atmospheric phenomena and secondary cosmic radiation, for verification of procedures and methods for atmospheric measurements, and also for testing of new devices in challenging conditions. Since 2015, we launched several stratospheric balloons. Almost every year, at least one balloon with various payloads. The overview of these flights is summarized in this table. So despite the generally successful nature of all flights and also the fact that gondolas were always found, different technologies were tested and tried to eliminate some partial shortcomings which emerged during balloon flights. The individual colors in the table represents a degree of reliability and success of used technologies. Dark green is the best fulfillment. Light green is fulfillment with some minor complications. And orange and red represent failures. So the used technologies have undergone intensive development from flight to flight. Important thing is, apart from recording and monitoring of various data, also the possibility to trace the balloon during the flight and quick recovery of the balloon gondola. So, and also the main construction criteria were some reliable transmission of information about the geographic location of the gondola, also good resistance to impact, and ensuring the function in temperatures far below zero. So when we were thinking about the development of suitable system, we were faced with several challenges. So better is to develop some flexible system rather than system is specialized only on one task, because usually we would like to measure different things, and flexible system is more versatile, but also more development intensive. Also, we would like to have possibility of measurements under unfavorable or even extreme weather conditions, and also use of real-time data to adjust the measuring process. So based on our experiences, we used during the last balloon flight the universal concept of avionics called TF-Atmon. So the avionics was implemented using UAV technology, Pixhawk autopilot with EX4 firmware. So DF-Atmon system that makes possible to connect different types of payloads and also carry out various atmospheric measurements. So it also provides devices, basic services such as power supply, time, position, and orientation information. The system is quite universal. Its infrastructure is designed for fast implementation of new sensors. It can be also used on various platforms based on specific needs, such as autogyro, multicopter, or balloon. Also, flight computer provides some possibility to record data from experiments in some common log file. Also, some basic quantities like temperature, pressure, humidity, magnetic field, and acceleration are also recorded and can be visualized. So the schematic diagram of this DF-Atmon system is shown on the right side of the slide. So the balloon gondola during the last flight was equipped with the supporting avionics, which has following features. So it enables simplification of payload integration. It also enables the use of payloads consuming several watts of power. It has redundant telemetry link. It enables gondola orientation tracking and logging, the power monitoring and maximal uptime calculation relevant to actual situation, and real-time pre-flight payload diagnostic. So, as I already said, the system was used and tested during the balloon flight week 6. So, this flight was launched in December 2020. We used balloon HUIV 1600 filled with helium and carrying the payload of about 2 kilograms. Expected maximum altitude was about 33 kilometers and total time of flight was about 1 hour and 40 minutes. So the goals of this flight were for scientific, means measurement, or some experiment for measuring vertical profiles of secondary cosmic radiation with various detectors, and also testing and verification of the developed platform and technologies, namely gondola trajectory and altitude logging and recording, functionality of the radio link used for telemetry and control, and also system reliability to use for control descent in some future experiments. So gondola equipment included, together with Pixhawk autopilot, also 3 different radiation detectors, 2 ion meters, 3 telemetry systems, and camera. And all devices were integrated into one functional unit with common power supply. So this balloon was launched from airport in Příbram in Central Bohemia and flew about more than 80 kilometers in eastern direction. So the whole path was covered by the data transmission. So both links modem and LoRa network worked for the whole duration of the flight. That means for almost 2 hours. So the rescue team followed the balloon along the flight trajectory, and the precision of tracking allowed actually to rescue the gondola within several minutes after touchdown. For recorded data analysis, we used Flight Review graphical tool, which could produce a graph from every recorded data. So here is shown an example of recording of acceleration at the moment of balloon burst. And in the bottom left figure, there is spectral density of vibrations. And we can see here the increase of vibration on the descent after the balloon burst. And on the right side, there is a screenshot of the 3D trajectory display. So in these graphs, there is shown examples of data measured during the whole flight. The system recorded temperature, pressure, humidity, and also radiation characteristics as histograms of deposited energy of radiation events from all 3 radiation sensors. So we can see that the maximum reach altitude was approximately 33 kilometers above sea level. And also we can see that the intensity of secondary cosmic radiation increases with increasing altitude, and at about 20 kilometers it reaches its maximum, called regional Flotsa maximum. And the balloon crossed this regional Flotsa maximum twice, so during ascent and also during descent. So as I already mentioned, so during this flight, 3 different types of ionizing radiation detectors were used. It was space DOS with silicon pin diode, R-DOS-C with small inorganic scintillation crystal coupled with silicon photomultiplier, and also Geiger-Miller tube. So by processing the data, graph of detected altitude was obtained. It's shown here in the right side. So the measured altitude of the regional Flotsa maximum was for all detectors around 19 kilometers above sea level. So it slightly differs based on the detector type. So as a conclusion, I would say that universal platform for atmospheric measurement using balloons or also UAV was developed, and it was successfully tested during the balloon flight week 6. The system proved to be useful for testing some cosmic radiation detectors. So telemetric system, DF-Atmon enables not only data recording, but also pre-flight instruments control and monitoring during the whole flight. And thanks to the availability of different communication interfaces on the basic avionics, the use of various alternative detectors is simplified, and this enables to measure various parameters, for example, electric field, ionizing radiation, atmospheric aerosol particles, and also supporting metadata like air pressure, humidity, temperature, vehicle acceleration, position, and absolute time, and so on. And also data can be visualized using different visualization techniques. So, and for future experiments, safety, system safety, and also the overall data collection effectivity could be significantly improved by implementing some controlled descent of the payload. And this descent can be carried out using some UAV, some autogyro carrying a payload. So this new technology would enable some selective measurement of defined or interesting layers in the atmosphere, and it also enables the selection of the safe landing area. So the idea or the solution is based on some rotograph DF-G2 autogyro that is designed to be able to fly also in strong winds, and it's easy to repair because most of the components are made using 3D printer, and it also allows relatively easy integration of payload. So, and thank you for your attention.
Thank you, Eva, for this talk. There was a question that I cannot see any longer, okay, because Andrei have responded. Anyway, the question was if TGF can be an issue also at ground level. I don't know, Eva, if you want to answer, or if we can ask Andrei.
Okay. So that, yeah, maybe Andrei can answer better than me. But
Yes, so replied already. So we haven't detected TGFs yet. We have detected TGE, yes, thunderstorm ground enhancement, and not terrestrial gamma ray flashes. But most of the TGFs has upper direction, so this is why they are detected on orbiting satellites. And some of them, so some short bursts were described and detected also on ground. But they have much lower intensities, yes. And but I have no experience with this, so sorry for that. Yes, but about the TGEs and about the peaks of radiation from thunderstorm radiation. So it will be in one of the following presentations, yes, by Martin and Jakub. So.
Okay, perfect. Thanks, Andrei.
Thank you for the question.
I cannot see other questions, so we can move to the next speaker, who is Martin Kakona. So, Martin, the floor is yours.
Thank you. Good afternoon, everybody. I have to say something about, let's say, thunderstorm chasing by cars and ground measurements by cars. Our motivation for this was more frequent the measurement of thunderstorm. And the second thing in situ measurement, yes. So because we want to measure the thunderstorm without interruption in the native.
Martin.
Sorry. You didn't hear
we
me?
don't know if you are speaking, but apparently we cannot neither see or hear you, just the presentation.
Sorry.
So maybe some of us can hear you. So I do hear you, and no problem.
Yeah, but is it possible to do some check if audience?
Actually, cannot. Okay. So it seems that for someone it works. So maybe it's just a problem of mine. So please go ahead.
Okay. That cars is equipped with a lot of sensors. Which can measure a lot of physical values around the thunderstorm. We can measure electric field or magnetic field produced by lightning, and we also capture some snaps or video how lightning looks. And we also measure a lot of atmospheric meteorological values. For instance, here is an example on the picture: distrometer, anemometer, and of course we can measure other values like atmospheric pressure and so on. And of course, our basic interest is measurement of radiation from thunderclouds, and for this we use the gamma spectrometers. which covers the energy range of photons from hundreds of kiloelectron volts up to tens of mega electron volts. There is a lot of auxiliary equipment inside the car. I have described only two of this. The triggering unit, which can trigger all devices by the lightning, the records from all devices by lightning, and GPS, which is responsible for time stamping of the event, so we can compare our measurement with many cars. And first, I have to say something about our radiation measurement. We do that measurement about 3 years, and we already measured more than 100 thunderstorms. So we have recorded around 1,000 of lightnings. 1,000 of lightning. So, but I have to say that we have no evidence of radiation from thunderclouds on the ground level. But with the similar setup, we have measurements of TGE on the top of the mountains with the highest elevation. Then we can reach in the Central Europe because we usually measure with our cars in the Czech Republic and the Slovak Republic. But of course, the question is why we didn't measure any increase of ionizing radiation on the ground. So the question is where and when the thunderclouds produce that radiation, that emanation. Now I have to turn your focus to only one special device, which is fast motion camera. We have mounted the full sky camera, and on the right side you can see the typical picture from such camera. This camera is facing up to zenith. So around that circle you can see the horizon. And please remember this picture because in the next slides I will show you some lightning captured by this camera, but that circle was invisible or almost invisible. Yeah, there is a typical capture of lightning, and this is a typical capture of lightning. But the lightning, which can be seen on that picture, is only that blue stain from up to down in that picture. So we developed some method how to proceed the data from the camera, and we calculate some curve and time, which is the sum of intensity or sum of illumination of all pixels on that camera. So the result is a red curve, and we can see that the increases and decreases the luminosity, which is from thunderstorm, from the lightning. And that graphs, that records, we can compare with the other devices. For instance, the top graph, there is a record from one of our antennas, and we can compare, and you can see the perfect correlation with the signal. And of course, there is different details of the lightning. Yes, and the second purpose of this graphs is this: we can compare different lightning from different thunderstorm, and as you can see, maybe there is some similarities in the lightning. The development of the lightning has the similar stages, and we can discuss which part of that graph is which phenomenon and the special part and the lightning. So maybe clear is this in this video. I were on it. Okay, there is a capture of one lightning which lasts 1 second. It is 1 second. You can see the time countdown at the down, and at the top there is a light curve, as I speak about it previously. And you can see how complicated the lightning is, how long this lightning lasts, and how big is that lightning, because you can imagine that you can lie on the ground and you can facing to the zenith, and your nose is pointing to the zenith, so you can see this if you are so fast. And I can see that you can see I can say that you can see the leaders. There is a small slowest part of that lightning, and fastest lights on the bricks. We call it recall leaders. Yeah. Yes, and that's a conclusion about this. What we can see from such data, and generally from our measurements by cars. First important thing is that only 10% or less than 10% of lightning produce cloud to ground lightning. So more than 90% of lightnings are only intercloud lightning. The second important thing is the duration of lightning. We can see that median duration is a half second. So it's maybe unusual for the people which is not interested in lightning. And the third thing, the lightning are huge. Our estimation is that the spreading, horizontal spreading or horizontal spread of the lightning is more than 15 kilometers, probably tens of kilometers. So some electric field, gradient of electric field must exist in horizontal layer in the thundercloud. So and this field is much stronger than vertical field, because the maximal altitude of the top of the thunderclouds is about 12 kilometers, and the base of thunderclouds is around 1 kilometer. So we are expecting the radiation emanation, the ionizing radiation in the horizontal layer, not in the vertical layer on the ground. And some other conclusion, because we are looking about TGF and TGE. TGE is too long for to have connected it with the particle lightning, yeah, because the lightning lasts about half second or maximally 1 or 2 seconds, but TGE can last minutes. Yeah, So probably the TGE is not in direct connection with the lightning, but with thundercloud it is. Yeah. And TGE, opposite of this, is very short. The length of TGF is only sub-milliseconds. So if we talk about the lightning only, there is only one phenomenon which can last the comparable time. It is recall leader. Yeah, so there are conclusions from our measurements from it. Thank you for attention, and I will try maybe the response some question in the chat if there will be, or maybe there is some time for the question.
Martin, there is a question by Rémi Galliard who says sub-millisecond is rather imprecise as TGF duration. Do you have more further information?
Imprecise? Yes. Yes. It is not clear yet, yeah, because if we quote about TGFs, which is recorded by satellites, we usually make the correlation 1.5 millisecond from the TGF detected by satellites, and from this. And from the satellite measurement, the TGF duration is 100 of microseconds up to 1.5 millisecond. But the TGFs, which was detected on the ground, was around microseconds and tens of microseconds. So it is a big mystery because there are not yet connection between the satellite data and the ground data. But I have to say that we have only the few detection of TGFs on the ground yet. Yeah, so it's still the question. And now we have to say only that TGF can last from microseconds up to the let's say 1.5 millisecond. But the question is if the measurement is correct. Maybe the TGFs is only pileups in satellites measurements. So the duration can be shorter because on the ground measurements we measured groups of microseconds and 10 microseconds passes.
Okay, thanks. I cannot see any other question, so we can move to the next speaker, who is Jakub Slag. Please, Jakub.
Hello, everybody. My name is Jakub Šlego, and I'm a PhD student of Ondřej. And I'd like to show you our measurements from high mountain observatories. And we started our network called GASTRON, Gamma Spectrometry of Thunderstorm Radiation Observatory Network. We have our spectrometers positioned on Milešovka in Czech Republic, also Poledník, in Slovakia in Lomnický štít, in Bulgaria in Musala, and also thanks to our friends from Eurados, we have our detectors on Zugspitze and Jungfraujoch. We plan to send one to Sentis, but due to some bureaucratic problems, we plan it for this year. And to show you what Milešovka Hill actually is, it's an old volcano core of the volcano, very old, not active, very long time, but it's a one hill, and it at elevation from the foot is 300 meters, and on top of that there's a professionally held man-stationed meteorological observatory. So we have very reliable meteorological data. And also I'd like to stress the point of Lomnický štít, and I will show you data from those two hills mainly. And now I'd like to show you what we measure and from data from Zugspitze. We already covered this, and because we are pressed by time, I will skip this. My colleagues already told you about Thunderstorm and DGF. This data from Zugspitze really shows what we are into when there's a rain only, no thunderstorm activity. We usually see peaks of radon progeny where they are in a range from 0 to 3 mega electron volts, and you can see it in the first peak, the red peak. The second one, however, has a thunderstorm activity at the beginning, and you see there was a rise in we call it thunderstorm area of energies from 3 to 9 mega electron volts, depending on the detector, how is it set up, and above 9 mega electron volts we call it like a cosmic energy range. And you can see from light green and dark green there were peaks also at those points, and we can look into it more deeply. Our detectors on Milešovka and also the Sevan, the Lomnický štít, there's stationed the Sevan detector, which is Armenian design, and it's a plastic type set of detectors. And from coincidences, when it's in between those layers, there's a layer of lead, and by coincidences, we can see that sometimes there's more lower energy particles, sometimes there are higher energy when it's like 0, 1, 0, and when it's like 1, 1, 1 or 1, 0, 1 from top bottom, we can see that it was a muon, because otherwise what would go through all of those and trigger those detectors. And it's 3 meters high, 1 meter times 1 meter, the whole area. And on the left side, you see the house we have on Milešovka for that. And our spectrometer, RT56, we also use growth that's developed by Yuki Wada and its colleagues from Japan. But I want to show you data from this detector, RT56, developed by Czech company CRREAT, and it has a 1024 channels primary spectrum, and also it has a secondary spectrum that can be placed according to our design, either around 511 keV or as a cosmic mode, which is above the primary spectrum, where it measures as a time over threshold how the signal from this event happened in the crystal has a duration above that threshold. Also, it's capable of timestamping every event that happens and it has its own batteries for one-day operation, because usually on those high mountain observatories, the weather is so severe that thunderstorm can shut down electricity, and at that point we really want to have data. This is from data from Lomnický štít. I want to stress out that these are preliminary data and happened in the last at the beginning of autumn. I have a mistake here. It was in September. Never mind. But we really are trying to, I want to show you here what are we dealing with and what are we playing with. On the top graph, there's a combination of RT spectrometer, primary spectrum flux, just summed up, and 7 top channel. And you see that the rise was about 500%, and then usual. And on the bottom, you see the data from electric field mail. It was a really strong negative electric field, which shows that there's a big possibility. We conclude from that there was a lower positive charge region in the thundercloud. And so from the upper negative cloud of charge, there was a really huge voltage that accelerated electrons downward toward the mountain, and by Bremsstrahlung we see those photon rise. And here is the compare of spectra. The green one is usual natural bounding at that spot, and the red one is this is taken from the highest flux minute of that event. The whole event lasted about 5 minutes, and the full duration at the half maximum of the peak was about 1.5 minutes. It was one of the strongest TGEs measured because Lomnický štít, it's really a pinnacle. It's a really sharp mountain, pointy one, and those electric fields up there are very strong. And from those curves, those spectra, we derived what was the expected original spectra. It's the orange curve. This is also from the same event, and I show you the data from 7. I show you the overall count rates in top, middle, and bottom channels. No coincidences, and you see that this also shows peak in the bottom channel, which is really huge, and either it means that there was so energical particles that penetrated both lead layers, or it came slightly from the side, which might be the issue here. And this is data from RT spectrometer cosmic spectrum. From at the right on top, you see from calculations Monte Carlo with FITS what are the results of muons entering the spectrometer, what should be expected by muons, and this spectrum is not yet linearized. So and at the bottom we can see there's some changes, some like fluctuations that need to be done, and we are working on that. But we see really excess at that minute of TGE, which is the red curve against the blue curve, which is the background on the bottom graph, and the subtraction is the green curve, and we see that those photons we detected might really come up to 40, 45, 50 mega electron volts, because the peak of muons releases about 55 mega electron volts in the scintillator. This is from another event that happened only a month ago on Mileshivka, which is first event after about 3 or 4 years, and during that we put our detectors there. So we have data from Sevan, data from Spectrometer, data from electric field mill, and I will also later show you data from Cloud Profiler, which is a radar pointing up. And this TGE was terminated by a lightning discharge, and we are now looking what really happened there, because it was an unusual winter thunderstorm, really low. The base of the thundercloud was about 60 meters above the observatory, and you can see on the green curve that because the spectrometer also counts number of pileups during every second measurement, there was a huge pileup peak, and but there's some data mismatch time on the spectrometer, so this is really preliminary, but we can see that it really shows something, and now we are looking to what can the Cloud Profiler show us. This is vertical, the green and red graphs are vertical velocities of air, the red going up, blue going down, and the cutout you see on the right side, and with the top channel of Sevan up, and the line shows 2320 of UT, the moment of the highest flux, and we are currently looking what was really going on. We see a really fast, well, for a winter thunderstorm, really fast updraft. It's the red peak on bottom of the Cloud Profiler data graph. And here is our colleagues from Institute of Atmospheric Physics, also from that data of the radar. They developed their code how to see what hydrometeor were up in the cloud. We see that the cloud was maximum was about 3 kilometers above the station, and that during those peaks of Sevan detector, we also have one preceding small peak that shows on the middle channel, corresponds to this light blue area or a red area, and in the bottom, if I can draw a line there. No, I see okay, I can get to it, but I think you can see it, and this shows a combination of ice, snow, graupel, and hail in combination. So we are now discussing what this could mean. Where were the layers of charge, and how it affected and created the TGE that we measured. And this with a picture of Lomnický štít. I'd like to show you some plans for our future to make a new Gastron stations, to get more data, to have more information and better understanding of those phenomena. And also we are looking for short-term events that were not shown here. And also we want to add more detectors to one station to see their combination. Thank you for your attention.
I cannot see any question in chat, so we can go straight to the last speaker, who is Marek Sommer. Please, Marek, floor is yours.
Okay, excellent. Andrzej said that he hears me. So good afternoon. My name is Marek Sommer, and I have prepared overview presentation about our space project, which were conducted during or in the CRREAT project. I will talk about 5 different projects or 5 missions, where the first 3 space DOS, ISS Socrat and Lucky 7 were already conducted, and Matryoshka and BioNM2 are under preparation. So I will start with space DOS at ISS. Yeah, here it is. So space DOS is a detector which was developed by Martin Kakona. It is an open source detector, which is in many ways similar to Liolin, which has already been used many times in the space missions. And one of the biggest advantages of space DOS is its very low power consumption. So it can last for months just solely on one battery. So this detector was placed at ISS during the 2 campaigns together. It was there for several months, and we have the data, and the data are now being analyzed, and the manuscript is under preparation. So hopefully soon we will be able to show the data and publish the data. The same detector was also deployed on a Russian CubeSat called Socrat R, which is a 3U CubeSat, and its main goal was to test a new generation of microprocessors and also the radiation detectors. So the same space DOS was deployed in there, and this CubeSat is still operational and functional, and we can still receive the data in theory. I mean, during the pandemic, it was quite difficult to get the data from the Russian side, and today it's probably going to be even harder, maybe even impossible, to get the data from Russian side. So the future of the data is quite unclear at this moment, but we hope we will get them one day. Interestingly, on the same rocket, there was another CubeSat called Lucky 7, which is a smaller CubeSat, 1U, it is a Czech CubeSat, which was built mainly from commercial off-shelf modules or components, and to reduce the cost and also the development time. The main goals, or the primary goal, was to test the electronics, GPS receiver, and communication system at orbit, and the secondary objective was the measurement of the space radiation. The radiation detector was commercially available module called X100/7, which is a cesium iodide scintillator coupled with pin diode. And we have managed to receive data from this detector, and we published it in 2 papers. The first paper focused mainly on describing the capabilities of the CubeSat Lucky 7 and comparison of the radiation measurements with models. And the second paper focused on monitoring or observation of drift of the South Atlantic anomaly. And now I would move to satellites or missions that have not been conducted yet or performed. The first one is Matryoshka 3, which is an experiment at ISS, and the idea is to use human phantom equipped with various detectors, mainly TLDs and other passive detectors. But our contribution, or our main contribution, is to equip it with 2 time-pix detectors. One should be on the surface of human phantom, and the second one inside of the human phantom. And the goal of this study is to analyze the radiation doses received by human organs, and also to move the Matryoshka phantom around the ISS, so it can create kind of a map, or dose map. So we have done a lot of work during the preparation of the time-pix detectors, and we focused on their downsides when used in space. The first one is that their setting needs to change according to the fluence. So we proposed an algorithm which would change dynamically the frame rate, so we can optimally measure high fluences at SAA and also low fluences of galactic cosmic rays. And then the second downside of mini-pix or time-pix detectors is the limitation of per-pixel calibration. So the classical per-pixel calibration is done with X-rays up to 60 kilo electron volts, and then it is extrapolated up to 800 or 900 kilo electron volts. But if you use this extrapolation even further, you will get very incorrect results. So we managed to come up with method of high energy per pixel calibration, which can be done with alpha source, americium alpha source, and we were able to move this threshold from 850 kilo electron volts up to approximately 1700 kilo electron volts. It depends on each pixel. And what we are focusing on now is the stability of per pixel calibration, because we noticed that after the per pixel calibration, the response looks perfect, but with the time it shifts a little bit by a couple of %. So we want to do some tests and measurements to explore more about this phenomenon. And the last space experiment is BioNM2, which is a biological experiment which should carry 75 mice on board. And our task is to support this biological experiment with dosimetric data. So we developed a set of detectors, which is called CHENDA, and it contains passive detectors, silicon pixel detector, space DOS, and LED spectrometer. The silicon pixel detector was developed at Faculty of Nuclear Sciences and Physical Engineering, Czech Technical University in Prague, and space DOS was developed at our institute by Martin, and LED spectrometer is being developed by our institute and also ESC Aerospace private company. So now I would like to describe how the LED spectrometer works. So it is a hybrid silicon scintillator LED spectrometer, which has 4 layers of silicon strips, which are in crisscross pattern. So we are able to estimate the incident angle of particles when the particles or particle travel through all layers. And in the middle, there is a plastic scintillator, with pulse shape discrimination capability, which basically allows us to discriminate high LET particles and low LET particles. It is coupled with 2 sets of silicon photomultipliers, and the size is approximately 2 centimeters squared and 6 millimeters thick. And in theory, this detector should give us complex information about the radiation field, because it's also neutron sensitive. And from previous bioemissions, it was estimated that the neutron dose neutron component was quite significant. So that is why we focused on neutrons. It should give us LET spectra without the need of conversion factors in theory. And that hence we should be able to calculate dose equivalent. The output of this project is the prototype of the detector itself, the LET spectrometer, and also the paper which describes the behavior of scintillator and silicon multiplier model. And we use this model for optimization of PSD algorithm, or PSD performance, basically. So that's the two outputs of this space project. And now I will come to conclusions. So conclusions are quite brief. We have 3 successful space missions: SpaceDOS at ISS, CRREAT R, and Lucky 7. Although from CRREAT we don't have much data, just fragments of data. But maybe one day we will have all the data. And another 2 missions are in, I would say, advanced state of progress. But of course, because of the current situation, their future is quite unclear and dark, I would say. So thank you very much for your attention.
Thanks a lot, Marek, for your talk. I cannot see any question in the chat. I have some problem with the audio. Okay. Maybe Marek can keep the microphone off. Okay, so if no question, I thanks again all the speakers and mostly the audience who attended this webinar. And I wrap up this webinar, the 12 Eurados webinar. Thanks a lot, everyone, for participating.